Been a postdoc in the Alembert Institute for 2 years. A great expert of numerical methods for interface tracking. So it's a pleasure to hear you talk about. Well, I let you take the time.
Yeah. Okay. Is the voice okay online? Okay. No, I have this one. Okay. Thank you for Stefan's nice introduction. And the title of today's presentation is the edge-based interface tracking method, the EBIT method, an alternative to WOF. I think this ambitious title did come from Stefan Zelatsky. I think it represents his thinking and opinions about this new interface tracking method. And before starting discussing about multi-phase flow simulations, I would like to take this chance to introduce some of my work during my PhD and my previous industrial position. And I obtained my PhD in aerospace engineering from Peking University, and the title of my thesis is Transonic Flutter Prediction by Linearized Euler and Linearized Navier-Stokes methods. So what is aeroelastic flutter? The flutter is a dynamic instability of an elastic structure caused by the interaction between the structural deflection and the unsteady aerodynamic force, and is a very dangerous phenomenon. And this movie about wind tunnel test show how the flutter can destroy an aircraft. So predicting the flutter onset during the design stage and avoid the flutter during the flight are very important tasks in the aviation industry. So here is a simplified explanation about the onset of flutter. The movie on the left shows the unsteady pressure distribution on the upper surface of a wind undergoing pitching motion. The work done by the fluid on the structure within one oscillating period can be computed based on these integrals. So due to the phase difference between the aerodynamic forces and the structural displacement, this integral can be larger, smaller, or equal to 0, which correspond to unstable, stable, and neutral stable scenarios respectively. So in a real elastic system, the situation is more complicated. The deformation of an elastic system can be expressed as the combination of its natural modes, where QH is the generalized coordinates. By assuming a linear dependence between the generalized force and the generalized coordinates, and then an exponential form for the type-dependent term, the governing equation of the elastic system can be reduced to the following pK equations. So given the generalized aerodynamic forces matrix capital Q relating the generalized force and the coordinates, the stability of the system can be determined based on the eigenvalue of these equations. So one of the most important tasks in flutter analysis is computing this capital Q with an accurate and efficient way. And this is the main object during my PhD, was implementing the linearized Euler and Navier-Stokes methods into a multi-block compressible solver and use them for flutter analysis in external flow. So in the linearized methods, the unsteady flow field is decomposed into a steady part and a harmonic variant unsteady part. If we only keep the zeros order and first order term in the original Navier-Stokes equations and replace the time derivative by the I omega factor, we then obtain these linearized Navier-Stokes equations for an unsteady flow field caused by the harmonic motion of the elastic structure. Solving the steady formulation is much more efficient way to obtain the generalized aerodynamic forces matrix. So I will conclude this part by a benchmark test to show how we can obtain from a flutter analysis. Let's consider a wind oscillation which is described by its first four natural modes. For a fixed free stream Mach number, the flutter analysis can produce this VG plot, which represents the variance of the system damping as a function of stream speed. So we can see as the speed is increased, only the damping of the first mode will become larger than 0, corresponding to the onset of the flutter, while the damping of the remaining modes are all stay smaller than 0. The point with 0 damping is called the flutter point. So the flutter analysis implies that the airplane should not fly faster than this flutter velocity to avoid the dangerous situation. Sometimes you may observe this oscillation during the flight when encountering turbulence, but don't worry about that because all the aircraft are designed to fly in this regime far away from this flutter point. So after my PhD, I joined a CFD software startup, and I was in charge the development of the aero elasticity modules for their commercial CFD software, which includes the implementation of the linearized method I was working on during my PhD and some other nonlinear methods for unsteady force computation. Besides, I also finished the module used for flutter analysis in turbomachinery. I was also interested in GPU acceleration, and I have successfully ported a legacy compressible solver to GPU by using OpenACC. The figure on the left shows the result for wind body configuration obtained with the solver run on a GPU. So the OpenACC is a high-level language based on compiler directives, is similar to OpenMP and user-friendly. And if you want to port some large legacy codes to GPU, the OpenACC may be a good start point. So after COVID, I decided to come back to academia, and I also changed my research topic to multiphase flow simulation, multiphase flows. So in the following part, I will discuss my project during my postdoc period about the EBIT method. Here are some present and former collaborators on this project. Leonardo Schickel is the previous postdoc who started this project, and Tianlong is the PhD who is using the EBIT method for phase change problems. So here is the outline of my presentation. First, I will give a brief introduction about the core algorithms for in the EBIT method, which includes the interface advection and and how to extend the existing 2D EBIT method to 3D. Then I will show how to couple the EBIT method to the Navier-Stokes equations for multiphase simulations. And part of the 3D results in our paper and some preliminary 3D results will be presented and followed by the conclusion. So an accurate and efficient interface checking method are very important in multiphase flow simulations. From capturing methods such as Wolf methods, the interface is described and reconstructed based on a Eulerian field, namely the color function. From checking methods, the interface is described by a series of Lagrangian markers and their connectivity. Here we propose a new interface checking method, the edge-based interface checking method, the EBIT method, trying to combine some advantages of these two types of methods. So the EBIT method is actually from checking method, but the markers are only located on the cell edge. And in the current version of the EBIT method, we also have some restrictions on the number of markers per cell edge. Since the markers are only limited to the cell edge, a reconstruction step is performed at the end of the interface advection to recompute the position of the markers on the cell edge. So by doing so, we can point the markers are pointed to the background Eulerian grid, which facilitates the parallelization of this method. Furthermore, the interface is known explicitly in the EBIT method, making the coupling with the boundary layer model for multiscale simulations more straightforward. In the 2D version of the EBIT method, a split scheme is used to advect the interface. The figures on the left shows the schematics for a one-dimensional marker interface advection along x direction. During the marker advection, the markers are classified into two types. The one on the cell edge parallel to the x direction is aligned marker. Here, and here. And another one on the edge perpendicular to the advection direction called the unaligned marker. And both the precision of the aligned marker and unaligned marker are computed based on this equation of motion. But after one step of advection, the unaligned marker is no longer on the cell edge. So a reconstruction step is performed to compute the new position of the unaligned marker on the cell edge, which is denoted by this red dot. So this whole procedure will repeat for the y direction to complete the whole advection step. So this figure shows the computation of the unaligned marker. So in order to improve the mass conservation, we use a circle fit instead of a straight line fit to compute the new position of the unaligned marker. So in our 2D version of EBIT method, the connectivity is described implicitly by the color vertex. And the value of color vertex indicates the phase in the corresponding regions. And they are also used to distinguish these two ambiguous configurations when there are 4 markers within one cell. So this color vertex will allow for thin film structures smaller than the grid size along the diagonal directions. The detailed algorithm for the evolving of the value of the color vertex is shown in our paper. So due to the restriction of number of markers on cell edge, topology change will take place automatically when 2 markers move into the same edge. This is also the only topology change mechanism in the current version of the EBIT method. The EBIT method is quite different to the traditional from checking methods, where an unsplit scheme is used to advect the markers. But we found that by using the split scheme, it facilitates the extension of the 2D EBIT method to 3D. So let's consider 3D advection in X direction. It can be decomposed into 2D advection problems on 2 cell faces in one cell. And the connectivity in the 3D space will be represented by the color vertex on 6 cube faces. Then all the subroutines used for the 2D advection, such as the circle fit and the evolution rule for the color vertex, can be fully reused in the 3D EBIT method. So in the EBIT method, the interface advection scheme is coupled with the Navier-Stokes equations in a simple way. Here we consider the incompressible Navier-Stokes equation in one fluid formulation. And the surface tension term is computed using this continuum surface force approach. And a volume fraction field can be computed based on the position of the markers and the value of the color vertex. Then the volume fraction field is used to approximate this Heaviside function for physical properties and to compute the surface tension using the generalized height function method. So both the 2D and 3D EBIT method has been implemented in the Basilisk platform. The source code of the 2D EBIT method and the test cases shown in our published papers are all uploaded to my sandbox. You can also run these test cases online by using the online servers of Basilisk. So feel free to try this code, and I will be very happy if I receive some suggestions and bug reports from you. And the 3D version will be also uploaded to the sandbox after we finish the paper submission. The code regarding to use EBIT method for phase change problems is in 10 sandbox, and if I have some free time, I will also try to refactor this part to make it more accessible to others. So here I will show some test cases used to validate the EBIT methods. In 2D case, the 2D cases are selected from our published papers, and more detail about the results, including the scalability of the methods and the comparison of the accuracy and efficiency between the simulation with and without adaptive image refinement can be also found in this paper. So the first test is a single vertex kinematic test. So an initial circular interface is stretched by the flow field described by this stream function. The interface will be stretched into a ligament and return to its initial position at the end of the simulation. These two figures show the results obtained with different methods. Good agreement can be observed for the interface line obtained with the EBIT method and the Wolf method on this mesh resolution. But we can see that the EBIT method based on a strict line fitting can produce phenomenal mesh rules. That's the reason why we want to use the circle fit to improve our very first version of the EBIT method. Here shows the mesh convergence study for this test, and mesh convergence result can be observed for the interface line. These two figures show the area error and shape error to demonstrate the mesh convergence. A first order convergence rate can be observed for the area error and the shape error for the EBIT method. This is still the single vertex test with a longer period, and the interface is stretched into a thin ligament at maximum deformation. At this mesh resolution, a slight shift can be observed for the EBIT method at the end of the simulation. But for the EBIT method with the straight line fit, the shift can be also observed even at the maximum deformation configuration. This is the mesh convergence study for this setup. When the mesh resolution is not high enough, we can see the ligament breakup due to the topology change mechanism in the EBIT method. These are the mesh convergence study based on the area error and shape error. So interestingly, we can observe a convergence rate larger than second order for the area error when the mesh is resolution is high. I think it's because in this setup, the interface is more close to a circle during the whole advection, so which brings some additional advantage to the circle fit, and I think that's the reason why we got this strange convergence behavior. And the following test is the Rayleigh-Taylor instability without surface tension. When a heavy fluid is on top of a lighter fluid, the perturbation on the interface will grow and eventually evolve into a mushroom-shaped interface. Here shows the interface line at different time instance obtained with the EBIT method and the Wolf method. In the early stage of the simulation, good agreement can be observed between the results with the EBIT method and Wolf method. But during the later stage of the simulation, when topology change occur, discrepancies can be observed in these roll-up regions. And the Wolf method tend to produce some small artifacts which is not observed in the result obtained with the EBIT method. Despite of this discrepancy in the roll-up regions, both these two methods present a good prediction for the uppermost and the lowermost position of the interface. Here shows the time evolution of the highest and lowest position of the interface, and excellent, as well as the results from other literatures. And excellent agreement can be observed between these numerical simulation results. So the third test case is the rising bubble under gravity, which come from the Basilisk website. The first setup corresponds to the bubble in the ellipsoidal regime. Both the 2D and the axisymmetric configuration has been investigated, and good agreement can be observed for the bubble shape at the end of the simulation and the time evolution of the bubble velocity. And the second setup corresponds to a bubble between the skirted and dimple cap regime. For the bulk region of the bubble, good agreement can be observed for the EBIT method and the Wolf method, but the volume obtained with the Wolf method is a little bit smaller than those obtained with the EBIT method, and the EBIT method shows a smoother skirt. For the rising velocity, small discrepancies can be observed at the end of the simulation, and the EBIT method shows a slightly stronger oscillation at the end of the simulation. So in the following part, some 3D test cases will be investigated. The 3D deformation test corresponds to the single vortex test in the 2D. And a spherical interface will be stretched into a thin film by this incompressible flow field and return to its initial position at the end of the simulation. And these figures shows the interface at different time instance obtained with the EBIT method and the Wolf method. We can observe some hole on the interface at maximum deformation for the Wolf method, and some small fragments at the left behind at the end of the simulation. But the EBIT method will produce a smoother interface in this setup. So as the mesh resolution is increased, the difference between these two methods becomes smaller, and they show a good agreement in qualitatively. We also validate the 3D EBIT method with the oscillating droplet under zero gravity case. LAMP present an analytic solution for the interface, for the initial interface described by the nth order Legendre polynomial. And here are the formulae for the oscillation frequency and the damping time scale in LAMP's analytic solution. And following the setup in Shin's paper, we consider the oscillation regarding to the second order Legendre polynomial. the time evolution of the maximum amplitude for different methods are shown in these two figures. So we can still see good agreement between the EBIT method and the Wolf method, and with the analytic solution. For the coarse mesh setup, we also can observe a smaller numerical damping for the EBIT method. So the last one is the 3D rising bubble test. Due to the buoyancy, similar to the 2D case, we will investigate it two setups. The first one still corresponds with larger surface tension, corresponds to the bubble in ellipsoidal regime. And the second one with smaller surface tension corresponds to the bubble in a dimpled cap regime. So a good agreement has been shown to the bubble shape at the end of the simulation for these two methods. For the first setup, for the time evolution of the rising velocity, the result obtained with the Wolf method is slightly lower than those obtained with the EBIT method under the for the mesh resolution under consideration. So for the bubble shape at the end of the simulation for the second test, phenomenon discrepancies can be observed for the rim region at the end of the simulation. And the EBIT method will produce a smoother rim at the end of the dimpled cap. So here again shows the evolution of the time evolution of the bubble rising velocity for different mesh resolution with different methods. So for a coarse mesh, oscillation of the rising velocity has been observed when the skirt structure is formed during the bubble rising. And discrepancies can be also observed for the results obtained with these methods. But as the mesh resolution is increased, we got a better agreement between these two methods. So to conclude today's presentation, I present the core algorithms for the EBIT method, which includes the interface advection and the extension from 2D to 3D, and the coupling with the Navier-Stokes equations for multiphase flow simulations. And some 2D result and some preliminary 3D result are also present. Here are some ongoing work and some perspectives about this project. Since we are still working on the 3D EBIT paper, so more serious test is still needed, such as the mesh convergence study and more quantitative results. And we also consider removing the restriction on number of markers per cell edge, which will allow for a fully controllable topology change and inherit the advantages from the traditional checking methods for multiscale simulations. On the other hand, Tian has used the EBIT method for phase change problem, and due to the good scalability of the EBIT method, we are also aiming to use this method for some 3D large-scale phase change simulations. So we are we are also working on some more advanced surface tension models, such as the integral methods in Popinase and Outerwood's paper, and try to couple it with the EBIT method to reduce the superior currents in the simulation. Okay, thank you for your attention and patience.
Okay, thank you, Jieyun. It will be difficult for me to ask questions for obvious reasons. Maybe someone in the room has questions, or maybe someone online has some questions. I started open the discussion box in the YouTube channel. Yes, Jianyang.
You mean in which case? Yeah. I think it depends on the physics we want to capture. But if we want to replace the small bubbles with some Lagrangian markers, maybe the Wolf method is a better choice because it can preserve this point, and we can then replace these small bubbles with the Lagrangian markers. But the EBIT method will remove this small structure automatically. Maybe this is still a disadvantage of the EBIT method in the current stage.
Yes.
Yes. Compared to the Wolf method, the EBIT method is a little bit less efficient due to some unknown reason. I don't know, but compared to the traditional from checking methods, I think the EBIT method is more efficient and it can be coupled to the adaptive mesh refinement by a more natural way.
So actually, in the current version, I think you have a constant level along the interface.
Yes.
Okay. And would it be difficult to allow for a change of level, of refinement level along the interface?
Based on my current analogy about the basilisk, I think it's not too difficult to change this, to remove this restriction on the mesh resolution level.
Okay. Okay. Well, no more. Oh, Jianyang.
Yeah. I think before I perform the circle fit, these 2 points have been eliminated by the automatic topology change algorithm. So we only have these 3 points and these 3 points for the circle fit.
No more questions? Okay.